So okay, in this tutorial we will basically give you a collection of problems and we will show you a little bit on how to approach this kind of problems, and we'll leave it up to you to solve the assignments, right, because that will give you much more practice and you can prepare for your tests and so on. So we showed a very uh, preliminary problem while teaching in the class where we looked into one of these timing diagrams. So if you remember, these are called timing diagrams. And essentially what is there in a timing diagram is for various inputs, various combination of inputs, you are actually showed that the inputs change with time. So this is a timing, that is why it is a timing diagram. X-axis is time, as you can see. The y-axis for the different inputs and outputs is the amplitude. So in this particular case, the amplitude is binary. It can either be 0 or 1. So let us look at this problem where you have a series of different inputs. Sometimes the inputs will not change. That's why for x, for example, you can see the inputs is fairly constant for a long amount of time. It changed once and then it is fairly constant for a longer amount of time, whereas y changes more frequently. You can see that y was static and then after some time it changed, but x did not change. So you can actually use this different combinations of x and y to guess what was the Boolean function or what was the underlying circuit that made this function or implementation of this f possible, right? So that would be the task for you, that given this kind of timing diagrams, can you come up with the circuit implementation of f, okay, or even the Boolean expression. If you know the Boolean expression, you can always find out the circuit implementation. So you can simply chunk out the timing diagram in terms of chunks where none of the inputs or the output changes, right? If the input will not change, output of course will not change, but none of the inputs change, right? So this could be the first chunk where both x and y are set to 0, right? So here, as you can see, x is equal to 0, y is equal to 0. So while dealing with this kind of problems, you should always write the truth table first. So you write x, you write y, these are the two inputs to your truth table, and then you also have this output f, okay. And we will try to see that how much of the information is available in the timing diagram. Timing diagram may not have all the information available. So if you have x equal to 0, y equal to 0, what does the timing diagram tell us? The timing diagram tells us that y is equal to f is equal to 1, right? So this is probably 1, yeah, this is 1, this is 0, okay. So here f is equal to 1, so you can write f is equal to 1. Next, let us see what is there. Let us take the next chunk. This is your next chunk, right? As I told you, do not look at the outputs, just look at any unique inputs, right? The input has changed, output may remain same, output may differ, that is not our problem. As long as I have a different input, we should chunk it out. So in this particular case, y has changed, although x has not changed, but it is going to be treated as a new input vector. So x is equal to 0, y is equal to 1, okay. In this case, f is equal to 1. So we will just note it down. This is unique, I have not seen it earlier. So x equal to 0, y is equal to 1, in that case f is equal to 1, okay. So the next one, again the output did not change, but the input has changed, right? Y has become 0 now and x has become 1 now, okay. So x has become 1, so 1 and 0. The output, as you can see, is still stuck at 1, okay. And then if you see the next one, y is equal to 1, x equal to 1, and the output is 0, right? F is equal to 0. So this is 1, this is 1, this is 0, okay. So this is the truth table. and as you can see, this is just opposite of your AND function, right? AND function, if you have x and y are both 1, you typically have f is equal to 1, otherwise 0. This is just the opposite of that, right? But you don't have to do that kind of a pattern matching. You can just follow the normal way. You have to treat it as a regular truth table and then do whatever simplifications you want to do. So in this case, if you want to design a circuit, you have to first write it in terms of your truth table, terms of your sum of products expression, and then do the general circuit design, right? It might not be a gate, for example, right? Not every timing diagram will be a gate. It could be more complicated than that, and you need to create that using a collection of gates. So if you just follow the regular recipe, this is going to be x bar, y bar. I am choosing these three mean terms plus x bar y plus x y bar. Okay, so you can do further simplification, and I'll leave this up to you. You can of course use your already available knowledge of Boolean algebra and do this kind of simplification. Okay, and then you can do x bar plus x y bar. Okay, and then you can convert this to x bar plus y bar, which is again nothing but x y whole bar, which is NAND gate, but that is not important. What is important is that the way that you are following these steps and doing it for any general circuit. Okay, it is NAND gate, it is directly observable. You do not have to derive this, but I wanted to not everything will be observable, right? So you need to know the basic strategy how to approach this kind of problems. One more problem here we have is this timing diagram. Again, you have to this is logic low, this is logic 1 high. Similarly, you have to put down the same thing, x, y and f. So first chunk for the inputs before it changes, x is equal to 0, y is equal to 1, right? So x is equal to 0, y is equal to 1, f is going to be equal to 0 here. So f is 0. Next part is this next input chunk. Here x is equal to 1, y is equal to 0, f is equal to 1. So x equal to 1, y equal to 0, f is equal to 1. The next input does change. This has changed. This remains constant. So y is equal to 0 again. In this particular part, x equal to 0 and f is equal to 1. So for 0 and 0, we get 1. The next one is again x equal to 1, y equal to 1 and f is equal to 0. So 1, 1 and this is 0. Okay, so you can try seeing, probably I do not directly see that there is a underlying gate. We can just write the mean terms, right? So these are the two mean terms that we need to choose. One is x y bar, the other one is x bar y bar. Is it correct? Yes. So this is going to be y bar, right? And then x plus x bar, which vanishes, which is again going to be y bar. So my observation was probably wrong. So you can see that it does not depend on x. So I did not notice this part, right? So if we just notice this particular part, right, you can see that it's actually y complement. It does not depend on x. So these are all just complementary, right? So you can use this kind of a minimization also to figure it out. Sometimes it might not strike if there is a larger problem or there are more variables. So you can try out these problems. It will be given as assignments. Okay, there could be more number of variables and you can try that out. So if I want you to do this particular problem, maybe I can try this out. So here there are three inputs.
So next problem that I don't get one.
Maybe I'll just do this and then I'll not solve it, right? So this is three inputs. So the inputs are x, y, z, and the output is f. And as I told you, we will basically chunk it off. So here all the x and y are constant, they do not change. Z changed right here. So z changed here. So this is x equal to 0, y equal to 0, z is equal to 0. So 0, 0, 0, this is 1, this is 0, f is equal to 1. So f is equal to 1. Okay. Similarly, you will do the rest of them. Okay, this is 0, x equal to 0, y is equal to 0, z is equal to 1, right? So I will not fill up the entire truth table. Maybe I'll, and this is f is equal to 0, f is equal to 0. Like that, you will keep on having these entries, right? So it might happen that you, first of all, you need to basically make sure that you do not have any ambiguous entries. That is something that you must check, right? So if some ambiguous entry is there, the functional specification is wrong. So somebody might give you a timing diagram which has, let's say 0, 0, 1, you have f equal to 0. I can recreate the same waveform, right? So this is x equal to 0, this is y is equal to 0, and this is z is equal to 1, right? So this part of the figure, right, this is some kind of a condition that we have already noted down. Okay, so in this case, say this is x equal to 0, y is equal to 0, z is equal to 1, and in this case, let's say this is continuing to be 1. Okay, let's say f is equal to 1. So this is a violation of your functional specification. So I know that for x equal to 0, y equal to 0, z is equal to 1, f is equal to 0, I have already told, right? This is inconsistent. Okay, so whoever is giving you the timing diagram, this is a wrong timing diagram because the functional specification itself is ambiguous. Okay, this cannot be the case. For the same inputs, you are going to have the same output every time. Okay, you might face this kind of a situation and you have to report that the timing specification is ambiguous. Okay, so this cannot happen. Either f is equal to 0 is true or f is equal to 1 is true. Either this is correct, this is wrong, or this is correct, this is wrong. Either one has to be there. Okay, so this is one case, okay, where you might have the same inputs repeated, the outputs has to be also repeated. If it is not the case, there is some issue. This is one thing. The other thing is, let us look at this problem where let us want to create a circuit for this. Here also we have these three inputs x, y, z, and I have f. Okay, similar things, chunk it off. Okay, so the first chunk is x equal to 0, y equal to 0, z equal to 0, f equal to 0. 0, 0, 0, 0, no issues. Here I have x equal to 1, x equal to 0, y equal to 0, z equal to 1, f is equal to 1. So 0, 0, 1 and 1. Next we have 0, we have 1, we have 0, we have 0. So 0, 1, 0, 0. Then we have 1, then we have 0, we have 1, then we have 1. So for 5, 1, 0, 1, we have output is equal to 1. Then we have 1, we have 1, we have 0, we have 1, right? So 1, 1, 0, we have 1. Then we have 1, 1, 1 and 1. So 1, 1, 1, output is also 1. Now if you see that there are three inputs, For a truth table, we will require to have all the combinations of inputs. We are going to have 8 rows, right? 2 to the power 3. But this timing diagram is insufficient, because in the last case it was, if I show you this timing diagram that we have done last time, if this was given, this is an ambiguous thing, and if it was correct, this should be redundant. Okay, because I have already provided this, I do not need this any more time. Here this is insufficient. Okay, why it is insufficient? I can very easily, by inspection, I can tell you that what are the things that are missing here. So this is 0, 1, 2, 3 is missing, min term 3 is missing, min term 4 is missing, this is 5, this is 6, this is 7, right? So 0, 1, 2, 5, 6 and 7. So M6 and M3 and M4 are missing, right? So you have to define what these inputs are, or they might say you do not care for any other inputs, the other inputs are redundant, are not really important for your system. They are typically called don't cares, right? So if you have 3, which is like 0, 1, 1, the output you really don't care. And if you are trying to solve a function minimization problem, you can either treat it as a 1 or 0 depending on whether you can group these elements together nicely, but in a K-map, for example. Okay, so 0, 1, 1 can be treated as a don't care condition. Similarly, if you want to use the fourth min term, which is 1, 0, 0, this could be also treated as a don't care condition. Okay, and depending on whether this don't care condition will help you or not, for that you need to check out the truth table. So if I want to do a truth table for this, then I have to choose, let's say, to draw this diagram, right? And in the diagram I have to have, on one side I can have, let's say, x, the other side could have yz, and yz is going to have these 4 different combinations in a gray code format, which is 0, 0, 0, 1, 1, 1, 1, 0, and x is also going to be 0 and 1. Okay, so now simply you have to put these values down. Okay, so the function was represented using this blue ink. I'll use this blue. So 0, 0, 0, 0, right? 0, 0, 1, 1, right? 0, 0, 1 is 1. 0, 1, 1. So x equal to 0, yz is 1. Okay, this is basically a don't care here. We will see, right? And then x equal to 0, yz is 1, 0. So it's 0, 1, 0. 0, 1, 0 is 0, right? Then you have 1, 0, 0, which is again a don't care condition. Then you have 1, 0, 1, which is 1. Then you have 1, 1, 1, which is again 1. Then you have 1, 1, 0, which is again 1, right? So now as you can see that indeed they might help you in grouping things better. So if you did not have these don't care conditions, you might have, either you are going to have an insufficient timing diagram, you will not be able to do the timing circuit, right? Because you do not have 2 entries in the truth table, or the person who is giving you the timing diagram may say that this is all the inputs that we are going to have. You do not have any more combinations that you are expecting. In that case, the remaining inputs could be used for used as don't care conditions, and you can do the grouping nicely. At least in this case, you can have a group that looks like this. You can have a group that maybe looks like this, and so on, right? This will make your circuit more simple. Okay, so we will give you some more problems, both circuits as well as timing diagrams, and you will be asked to have a simpler implementation for them. Okay.